So you'll notice that we are moving back to a chapter 3 now, like we talked about. Chapter 1 and 2 and 9 were all under the heading of descriptive statistics. And now we're going to go back and talk a little bit about probability to get us ready to move over to the branch of inferential statistics. Rather than just describing things that are known or have happened, we're moving on to making inferences, drawing conclusions. And when we do that, we probably want to be correct. So that's where the notion of probability comes in. We want to keep high probabilities, high chances of being correct. So a little dose of probabilities. Any other last things come to mind before we dig in? All right, well, probably already have, but if not, let's put the other phones and whatnot away so we can give the paper our full attention together. And I'll give you a minute to check out these first 3 definitions. Actually, there are kind of 4 words snuck in there. We've got 1, 2, 3, 4. 4 new things to check out. You happen to study probability before at all? Sometimes folks happen to see it, others don't. No big deal either way. We'll start with the basics and things we definitely need to know about. So a lot of times in probability experiments, something is repeated multiple times, and each time it's repeated, we call that a trial. So you might say, there were 10 trials, we repeated something 10 times. And the result of each trial is technically called the outcome. No big surprise there, probably, right? If we had a list of all of the possible outcomes for an experiment, we call that master list the sample space. And this is a kind of an official mathematical set. So we would technically or typically see each item listed out individually, like each possible outcome. And we'd see a comma between each of those possible outcomes and a set of braces around the outside. So that makes it sort of an official mathematical set. And being sample space, sometimes you'll see a big capital S out in front of it. So we're generally interested in particular outcomes. Maybe it's just one particular outcome, or maybe it's a group of a couple. Anything like that we're focused on would be the event of interest. So the event, again, could just be one of the possible outcomes, or could be multiples, could be a couple. We've got a little scenario down here to help us start to get used to that lingo a little bit more. Do you see anything for right off you'd like to ask about it, though? All right, so let's imagine that we had a single die, right, out of a pair of dice. Maybe we had just one of the two, and we're going to roll it. See if you can think what the possible outcomes would be and what that means the sample space would look like, and consider possible events we might be interested in. Let's see what has stuck and makes sense so far. Give you a second to give it a try, and then we'll talk it through. So not 2 dice, but just one of the 2. What could you get when you roll it? Yeah, what are you thinking, Cole?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. Excellent. So possible outcomes 1 through 6. If we're going to make that kind of official sample space, we would do more like Colton said and list them out individually. 1, 2, 3, 4, 5, 6. And then we want to use some of the same notation here. So commas in between them all. And these big fancy curly braces around the outside. It's not really a totally different answer from number 1. We're just listing it a little more officially with set notation. Sounds like a great start. Were others thinking along those lines? Roll a die, you get a 1, 2, 3, 4, 5, or a 6. So out of all those possible rolls, there's different events we could be interested in. Maybe we're just interested in knowing if someone rolled a 1 or not. If I put the big capital S out in front of that, I might see a big capital E out in front of this. Excuse me. S for sample space, E for event. So any one of these outcomes could be the event that we're interested in, like rolling a 1. Or maybe multiple possible outcomes grouped together is the event we're interested in. Is anybody thinking of any other possible events out of this subspace? Rolling, let's say rolling an even number. That's going to be more than one outcome. Out of the sample space here, rolling an even number would include what? It would include the 2 and the 4 and the 6. Yeah, so that'd be another possible event. Any subgroup of our sample space could be an event we're interested in. So it's just sort of kind of a made-up example to give us something to work with. I don't know how many people really study rolling 1s or rolling evens, but something pretty simple we can start with. So each of these outcomes are going to have probabilities associated with them, like how likely they are. And we'll be getting into how to calculate those in just a sec. I wanted to mention first, though, that based on what information we use, they could have different names. So these are really all types of probability. They're all calculated the same way. It's more about where the information comes from. Like if we conduct an experiment and use those results to calculate our probability, it might be called empirical or experimental. We don't have to know these words inside and out, but it helps us to think about the different ways we could get our information. If we don't conduct an experiment, but maybe base our information on a theory instead, we could call that a classical or theoretical probability. And lastly, if we don't have either of those, but are working with an educated guess, we could have a subjective probability. So again, they're all calculated the same way, just a little bit different. Like with rolling the die, we don't actually have to roll the die to know what the possible outcomes are and to calculate their probabilities. So that would fall under theoretical. It's not to say you couldn't roll the die, but we know in theory exactly how it's made up and whether it's a evenly weighted or a weighted die, perhaps. On the other hand, if there's something we don't have a theory for, but we really need to experiment and see what happens, that information will be a little bit different. Like maybe we were trying to study traffic patterns. There's no theory that determines exactly how traffic is going to flow. Maybe we have to watch and see what happens before we know the rules of the game, know when to expect a big rush or a quiet time. One way that we can definitely distinguish these two is to think about the results. Like if we base our ideas on the theory of rolling a die, we should get the same results every time. So with a theory, the results should not vary. Results should always be the same. On the other hand, if we're watching cars work through an intersection, each time we go out and watch, they could vary a little bit. The results could vary if we're conducting an experiment instead of just using theory. Yeah.
So rolling a die, the results are the same?
I was saying if we don't actually roll it, but we just base it on the theory. So maybe rolling's not the right word. Maybe we'll just say a die. How about that? Yeah, think about the outcomes you could get if you rolled the die. Good point. Working with a theory, we should get the same results every time. On the other hand, if we're conducting an experiment, the results are going to vary a little bit each time. Okay, probability is actually pretty straightforward. We just need two numbers and we're going to divide them. Kind of like getting leading up to a percent or a proportion. Two numbers that get divided. So if you're ready to see a little more about that, we can flip on over. We've got a formula on the next page. Anybody see anything they'd like to maybe double check or talk a bit more on the front page first though?
Yeah. Going over objective.
Yeah, I didn't give an example of that, but that's going to be kind of different if you're just maybe using your knowledge and making the best guess you can.
Okay.
We don't tend to see subjective as much. It's not quite as reliable. Yeah, formula is going to look probably way more complicated than it is. The actual calculation comes over here on the right side. So I mentioned that we need two numbers and we're going to divide them. That's really what it boils down to. If you've ever talked about like the part versus the whole with a proportion or percent, it's a very similar idea. So we're always thinking about the total number of possible outcomes, like how many things were in our sample space as the bottom number, what we're dividing by. And then out of that, we're looking to see how many of the outcomes fit our criteria, like are part of the event we're interested in. It says favorable there, but that doesn't particularly mean it's a good thing versus a bad thing. Favorable just as in that's what we're studying. That's what we're looking for. So the total numbers on the bottom, the number of outcomes that fit our criteria is on the top, and we just do a little dividing. So the number of outcomes in the event, we could say, divided by the number of outcomes in the sample space. The dividing, we're going to get decimals, or perhaps once in a while leave the answer as a fraction. If they're real nice, easy numbers, we might leave an answer like 1/2, but otherwise we're usually making a decimal. And typically we're asked to round them to 3 places. So we'll be doing lots of thousandths throughout the chapter here. Up in our formula box, I also wanted to mention what's going on the left side of the equal sign. This is just our label, really. If someone were to see this out in front of our work or our answer, they would know that they're getting ready to look at the probability of an event. So the P there stands for probability. In math, when we see the parenthesis, we usually interpret it as the word of. This parenthesis, by the way, doesn't mean we're multiplying. We're not taking some P number times some E number. It's just a label indicating that whatever's happening on the right side represents the probability of an event. A little bit of labeling notation we'll use along the way and try to get used to. You can see some of it in action already right here. So the P on the outside for probability, and then inside, notice it actually describes the event. That's more typical of what we'll see. So in that case, we're going to be looking to figure the probability of a 4 when we roll a single die. So just labeling over on the left, the actual formula, dividing's over on the right. Anything you want to ask about it in general before we try it out some with our die? Our single die, where we said the sample space was 1 through 6. And we're going to find some probabilities of different events here. Well, let me give you a minute to start thinking about some answers. I think these are going to be pretty nice numbers. I'm probably going to leave my answer as a fraction. But we could look at it as a decimal too, in case you want to practice both. So whatever's in the parentheses is letting us know what the event is, what we're interested in. A little bit like learning a new language, isn't it? Lots of new lingo. Well, let's check in on this first one. Out of all the possible things we can roll on a die, how many of them are 4? It's just the one, isn't it? So 1 possible out of 6 total makes that probability 1/6. You got it. The event in this case is just 4. So there's only 1 outcome in that event versus the 6 total, 1/6. How about as a decimal? Did anybody do that?
0.167.
0.167. Great. 6, 7. On the calculator, by the way, if you divide something like this and would like to turn it back into a fraction, you can do that with the math button. So if you don't already have that on your screen, you might do something like 1 divided by 6 and get that decimal answer. Then I'll show you how we can use the math button to turn it back into a reduced fraction. This one already started as reduced fraction, so it may not be real revealing. However, with other numbers, might be handy. So with a decimal already on there, I'm going to press math and choose that first option that's going to turn it into a fraction. So the arrow and the frac. And when I enter again, I get the reduced fraction back. Might be helpful at some point. If anybody sees anything they'd like to double check about our first probability, let me know. Otherwise, I'll give you another minute to try the next couple. Anybody need more help on anything so far? So we can see inside the parentheses, the next event we're interested in is rolling an even number. Think about how many possibilities that has versus how many possibilities total on the die. What do you guys think for the probability of rolling an even number?
6.
3, 6? 3 even numbers out of 6 total? Yeah, so 3 out of 6, maybe 1/2 or maybe 0.5 then? Yeah, event in that case would include the 2 and the 4 and the 6. We mentioned on the previous page. Sounding like a great start. Our next event is described a little bit differently. Looks like they're using the variable x to represent the roll. So we're interested in rolls that are greater than 5. What could you roll that would be greater than 5? 6? Yeah, should we not include 5 in that? No, there's no equal bar, right? Just strictly greater than. So that's 1 out of 6 again, 1/6. 0.167. Yeah, last two are a little strange. You get maybe a little bit of a weird answer. Anything we can help out with on part C? So we're interested next in a number less than 7. What could you roll that would be less than 7? All of them, yeah. So in this case, the event is the entire sample space. So are you thinking 6 out of 6? And what would that look like when we reduce it and clean it up? So just 1, right? Since that represents 100% of our outcomes, 6 divided by 6 makes 1. Do you think you could ever have a probability bigger than that? Could your event be somehow bigger than your sample space? No, because the sample space is the whole list, right? So we're seeing here the biggest possible probability. If the event is 100% of our sample space, probability of 1. In other words, you are definitely going to get a number less than 7 if you roll a die. So 1's the biggest possible probability. Think we can help out with there? 6 divided by 6 makes 1. So what could you roll on a die that would be less than 0? Can you roll a 0 on a die?
No.
No. Is 0 less than? You can't roll anything, can you? That would be less than 0, like negative. So I'm saying there's nothing in the event. What would that mean about the probability? What are you going to divide by 6? If there's nothing that fits the criteria, 0 divided by 6, and what does that make? It does. 0 divided by 6 makes 0. Do you think you could get a probability answer smaller than that? No. So we're seeing the range now, right? From 0 at the low end to 1 at the high end, and then all of the fractions and decimals in between. So we'll get used to our formula and the notion of probability a little bit. Anything we could help out with on that example so far? So another new term we want to be familiar with is something called the complement of an event. Complement with an E in the middle, not an I, not like, hi, you look nice today kind of compliment. Different sort of compliment. Let me give you a minute to see what it says there. Let it start to sink in. And then as an example, let's start with the event of all even numbers. All the even numbers you can roll. So if 2, 4, and 6 are in the original event E, what would that leave to be in the complement of E? 1, 3, and 5, yeah. So the complement has this little apostrophe on it, or sometimes it has a bar, like we saw with our regression equation. Our book uses the apostrophe. So here was the original event E, and now here's the complement of E. How would you describe it? What's the complement really? It's just all the rest, everything that wasn't in E? Yeah. So if I put E and the complement together, I should have the whole sample space, in other words. So the complement of E is the set of outcomes from the sample space that are not in E. So it's all the rest. In a way, it's kind of an opposite, right? Like the rest or the opposite of what you started with. There's one more statement here that we'll make use of a lot, and that is the probabilities of complementary events add up to 1. So if I have some event E, and I know its probability, and I'm thinking maybe about the complement of E and its probability, those two probabilities always add up to 1. That's what it's saying. And if you think about it, that might kind of make sense, because between E and E complement, that makes the entire sample space. So when we put them back together, we get 100% of our outcomes again. Up here, we found that the probability of an even number is 1/2. So the probability of even right here is 1/2. What would that mean the probability of an odd has to be if those two are going to add up to 1? It would have to also be 1/2, wouldn't it? So not that we couldn't calculate that on its own, but knowing it's the opposite or rest of the events versus the evens helps us find that missing number. We use it in fact like this a lot. The probability of the complement of an event is going to be 1 minus the probability of the event itself. Right? If these two things add up to 1, then I could subtract either one of them from 1 to find the other. Just like I could subtract 1/2 from 1 to find this missing number. Complementary events is something we'll see a little bit more of down the road. For now, we want to kind of start getting used to the definition and be able to answer questions like this. When we get our homework paper out, we can find something similar. Even like this number 3 right here. See anything they like to ask in general about the complement idea before we check on this number 3? So they've given us the probability that something will happen, and then they're asking us to find the probability that it won't happen. So that should be like the rest of the outcomes or the opposite of the original event. Can you tell what that probability would have to be? 34 out of 37 is the probability that it will happen. What out of 37 would then be the probability that it won't happen? It's the rest, right? The other 3. So these are complementary events, kind of like opposites. The 2 numbers there should add up to 1. So between the 2 top numbers, all 37 should be represented. That's a type of question we'll see right off about complements. Anything we could help out with on that one? I think our fraction trick would work here. If I took 1 minus 34 out of 37, gonna get some funky looking decimal, which we can turn back into a fraction. 1 and 2? Yeah.
Take 1 and minus, like, parentheses, 34 divided by 37.
And kind of like this?
Yes.
Yeah, that's exactly it. And that makes 3 out of 37?
Yeah.
Yeah. Sounds like you got it. Great. Anything else we can help out with there so far? Well, we'll keep that homework paper handy for later. And play a little game. Are we familiar with rock, paper, scissors?
Never heard of it.
Never heard of it? Well, your partner hopefully will be able to explain it to you. Rock, paper, scissors. We've got folks pretty well lined up. We've got partner, 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 cross. Probably think you mind moving over one to help us partner up. And what we like to do with your partner is play 24 rounds, 24 trials of rock, paper, scissors. Do feel free to ask around if you need any help with the rules of the game. Otherwise, as you go, keep track of when you win and when your opponent wins, and if you have any ties out of your 24 times. Let me know if you need help getting partnered up or getting started.
Twenty-four times. If there's a tie, I'll keep track of the topics. Yeah. Rock, paper, scissors, shoot. Rock, paper, scissors, shoot. Rock, paper, scissors, shoot.
I think how many times you tie.
Tie. One. Oh. Oh.
I know.
That's, we're at 9. Yep. Rock, paper, scissors, shoot. 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 For real.
Yeah, well, I got it.
Rock, paper, scissors, shoot.
I want to get over here.
Rock, paper, scissors, shoot. Rock, paper, scissors, shoot.
What was that, 20?
Yeah, 20. Rock, paper, scissors, shoot. 9. Rock, paper, scissors, shoot. Three.
You won by round.
Sounds like the names are dying down into your 24. Once you have that data, you could try answering the following questions, 2, 3, and 4.
Oh, yeah. Get a lot of time.
9 your wins, 5 my wins, and 10 ties.
Yes. Miracle.
I have 8. Yeah, I got right there. No, wait. So.
So I think for it to be a fair game, there'd be an equal number of wins and ties.
Oh, I get what you mean.
So helps get those 3 questions answered. When you get to part 2, you can stop for now. So just the top half of the page, what we're after. We all have the same numbers. Did player A win the same number of times for everybody? No, those are gonna vary, aren't they? When I played last, I came out with a 10 and a 12 and a 2. You may have had totally different arrangement. Do we have anybody that's really good? Because there's like a national championship. We could send you along. You and your rock, paper, scissors skills could represent us. Well, based on playing the game, do folks feel like it's a fair game? Yeah, lots of yeses. Did anybody feel like a no instead? Didn't feel so fair? Yeah. Yeah. Any maybes? Any other thoughts? So based on these numbers, what would the probability of player A winning be? 10 over 24? Yeah. Now I could reduce that or make a decimal just to keep it easy. Let's do that. And then player B with these numbers would be 12 24ths, and tie in this case would be 2 24ths. I'm calling these empirical probabilities. Why? Why am I calling them empirical? We actually played the game, right? That was our experiment. And if you and your partner played the game again, would you get the exact same results? No, they're gonna vary. Yeah, it was based on the experiment, the game. And it will vary. So we're approaching rock, paper, scissors from an empirical perspective so far. Trying to squeeze all the fun out of a game, right? Turn it into a math problem. At the bottom of the page, we're going to approach the same game from a classical or theoretical perspective. Anything we want to double check or say more about the top half? So kind of keep that in mind as we move on down. And to approach it theoretically, I've got a perhaps crazy looking chart right here. See if you can make any sense out of what's happening. Player A is represented on the side here. Player A could show rock, or paper, or scissors. Player B is represented up at the top. Also could show rock, or paper, or scissors. Why is there a T right there? Tie? Yeah, because they both showed rock. So we're thinking about matching up the possible combinations. Rock versus rock would be a tie. Rock versus paper, who would win? Paper would win, so player B. Yeah, that one's always been weird to me, that a paper would wrap up a rock and that'd be the end of it. But that's the rule, right? So could you keep making those matchups and put in an A or a B or a T, depending who would win or if it would be a tie? Okay, so we'll help get started there. Feel free to take it away to partner. No dynamite. Does anybody play with dynamite? No. Sometimes people put make that an option in the game,
Oh,
but I didn't go for that.
I've heard shoot. But not to. Yeah, whenever my friend is annoying, he says, shoot, I win.
Okay,
Because he shot me, I guess.
yeah, that sounds kind of dynamite-ish, doesn't it? Cool. I had a student from Great Britain one time and she held her paper this way. You usually hold your paper that way?
Yeah.
Yeah, she held it this way. It's more vicious that way, I guess, maybe, right? Gotta wrap up that rock.
Yeah.
So, what would we want here? Does rock or scissors win?
Hey,
Rock wins, so that would be an A. So TBA across the front, top row there. To be announced. How are the letters gonna come out in the second row then? It goes ATB, alrighty. Do you need a little help figuring out what's going on or catching up with us there? And then how about across that last row? It's gonna spell bat. B-A-T. So with these theoretical results, could you calculate the classical probabilities for A winning or B winning or a tie? And based on that, decide if you think it looks like a fair game still or not? I'll give you a minute. So in the results here, how many A's are there? 1, 2, 3. Okay, so 3 times out of how many total? 9. A wins. So we're thinking 3/9 or 1/3 or 0.333. How about for player B? What'd you get this time? 1/3 again. So there were also 3 B's. 1, 2, 3 out of the 9. Great. And what about the probability of a tie? Also 1/3. T, 3 out of 9. Do you notice what these 3 probabilities add up to? They represent 100% because they add up to 1. Yeah, nice. Between those 3, we have every possibility represented, kind of like our complementary events. They should add up to 1. Well, with the theoretical or classical probabilities here, what are we thinking about the fair game question now? We had lots of yeses before. The actual definition of a fair game is where each player has the equal chance of winning. So could we meet that criteria? Is it technically or theoretically true here that player A and player B have the same chance of winning? 1/3, 1/3. They were the same, weren't they? So it meets the official definition. If each player has an equal chance of winning, that's officially a fair game, which we kind of suspected a lot of folks earlier. I hear a lot of pages flipping, but there is one last detail I want to add there. Any last things anybody would like to add to it or ask about it first? So are you surprised that we didn't all get 1/3, 1/3, 1/3 when we played the game? Shouldn't you just get 1/3 every time? No, remember we said the experiment is going to vary every time, but it's probably going to level out at some point. Do you think playing the game 24 times is a lot of trials?
No.
It did feel like a lot, and some people are like, oh yeah, we're here all day. Would 2,400 be even more? Or 24 million? Maybe before Thursday, you could play 24 million times and keep track of your results? No? Okay.
I'll pass.
Well, the idea is, there's something behind the scenes here called the law of large numbers. I've told you, math folks aren't real creative, so this is the name they came up with, law of large numbers. That has to do with exactly what we've been talking about. It's not surprising that these didn't come out exactly the same. But the more we play the game, the closer these results should get to the theoretical numbers. If we did play 24 million times and keep track, those probabilities should get closer to a third, a third, a third. Law of large numbers. The larger the sample, the more times you play the game, the closer these will come to the theoretical numbers. 24 is not an awful big number, right? If we added everyone's results together, in fact, it would probably start to level out more and get closer to a third, a third, a third. So it's kind of a big rule behind the scenes, right? The empirical probabilities are going to approach the theoretical probabilities the more the experiment is repeated. Law of large numbers, yeah.
Would be 50% if we added up like each of our 33.3. If we added up his number and my number and her number and her number.
Yeah. If we pooled everyone's results, I bet our numbers would come closer to a third.
Yeah.
Yeah. No guarantee we hit it exactly yet, right? But it would probably be closer.
Would that take too long?
Oh, so we put that to the test? Let's see, let's get everybody's player A numbers. What y'all have for player A? 9, and for player A, you'll have 9 as well, and 7 and 7. Oh, look at that. There's our champion. And for 8, 8, and for A, 8 again. Alrighty. And for A, 6. And Amy and Paige, y'all were. What'd you have for A? I'm gonna have to ask you to put your phones away. Yeah. And for player A, 8, and for player A, 4. 8 and 4. All right. Somebody add all those up for us, and then we'll get our B numbers. B was
5.
5, and B was 8 and another 8. Okay, and 8 again. 5. A lot of 8s in here, aren't there? That's a third. Yeah. 8, 9, and 6 and 11. All righty, and 7. All right. Oh, sorry. There we go. So we're looking to add all of the A's, all of the B's. I did it off the screen where you couldn't even see, didn't I? Plus 9, 7, 16.
Player B, I have 87.
Okay. Me too. So let's see, that would be out of 24 times. Am I thinking right? Yeah. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 240. Look how close that's getting. So by adding them all together, we did get even closer to the 0.33.
What do we add up? 11, actually.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, what? Huh, oh, my numbers were in there. Okay, right, out of 11. Gotcha. So we need
24 times 11 and a 7.
Even closer. Nice. Law of large numbers is proving true. So any last thoughts on that page? Yeah, if anybody like to add to what we've been saying or ask about to clear up? I think we're right at our break time, aren't we? So we'll get going again in 10 minutes. let's start to come back together. Put the bolts and laptops back aside for now. See what's next with our probability. But I noticed a couple of things along the way that are always true about probabilities. And they're pretty much summarized here on the next page in the probability rules. So let me give you a second to check out these 4 things. When we talk about rules in math, we generally mean things that are always true, right? We're not trying to impose rules. We're just noticing things that are always true and calling them rules. Like we saw a little earlier on that a probability could be as low as 0 or as high as 1. And typically it's going to just range somewhere in between. What would you say is the which end of the scale here is the numbers that are more likely? Things that are more likely would have probabilities closer to 1. Yeah, more likely, closer to 1. And things that are less likely would be down on the other end, closer to 0. 0.5 would be smack dab in the middle. So 0 being the lowest possible probability means that an event is impossible. A probability of 0 means it's not happening. Like we're not going to roll a number on the die and get a negative. And then on the other end of the spectrum, a probability of 1 means something is guaranteed to happen. If I roll a die, I'm guaranteed to get a number less than 7. Most things range somewhere in between. And we've also started to see that we can add up probabilities within the same sample space. If we have every outcome represented, the total should be 1. Like the probability of A winning and B winning and ties added up to 1. Didn't leave room for that, did I? And the probability of an event and its complement add up to 1. We have every possible outcome represented among the events. Those probabilities should all add up to 1. Anything you want to maybe clear up on any of the rules or things that are always true about probabilities? Well, let's see a homework question kind of like this, where they throw out some different numbers and basically just trying to ask if it would be a possible probability or not. In this case, we're trying to see which of the following would not or could not be a probability. So based on what we know, let's see if you can spot any numbers there that would never come up as the probability of something. Double check on any of the rules. I think I already asked that, didn't I? Anything here jump out at you as an impossible probability?
All negatives.
All the negatives, yeah. So D would be out. B would be out. Is that all the negatives? Yeah, neither of those could be.
And 112.
112. So in addition to all the negatives, what else are we kind of looking for? All of the ones that are bigger than 100%, or in a probability language, bigger than 1. Any others that would meet that? Any others that are too big? F, 1.45, yeah. So 1/3 would be possible, 1 would be possible, 0 would be possible, 0.8 would be possible. I would take a little bit of exception to H and maybe say as 0.33 it would be fine. But our book is okay with the percent, so we'll leave that as a possibility also. Basically just trying to throw out anything that's too big, like over 1, and anything that's too small, as in negative. Anything we want to double check about that? All right, well, we've seen that calculating probabilities comes down to knowing how many of something there are. And one way to find out how many outcomes an event has is with something called a tree diagram. So it's a visual display, a diagram showing all possible outcomes for an experiment. By drawing the diagram, we can then count up and see how many possible outcomes a situation would have. And for starters, we're going to try making a tree diagram for the possible outcomes if you tossed 2 quarters. So we'll just let all that sink in for a sec. If you've studied statistics, probability before, you might have made tree diagrams. They don't tend to come up in other classes so much though. So you might have seen similar diagrams in other classes, but pay close attention because they might be a little bit different. Well, the tree's going to grow from a root. Doesn't exactly matter which direction it goes. I think I'm going to grow my tree to the right just because of the paper here. So not instead of this, I'm going to grow it like this. So from that root, let's think about breaking the 2 quarters down into parts. In other words, let's think about the first quarter separate from the second quarter. We're going to try to take the whole thing and break it down into a series of events, like considering the 2 quarters separately. So if you toss a quarter, that first one, what could you get? Heads, or you could get tails. So from the root, let's draw 2 branches representing the first quarter. Could be heads or could be tails. You'll sometimes on tree diagrams even see probabilities. We don't tend to see this as much, but we do know these are equally likely. So it'll be possible you'd see a 0.5 on each branch. It's not something we have to fill in, but just in case you look around at other tree diagrams. And now from these branches, we'd like to branch off again, showing what could then happen with the second quarter. Like say, for instance, the first quarter was heads. What could then happen with the second quarter? Could it still be heads? Could it still be tails? So from that heads branch, let's branch off again, heads or tails for the second quarter. If someone were to go back to the root and follow all the different paths through the branches, we'd end up finding all the possible combinations. Well, we'll come back to that idea in just a second. Let's say the first quarter was tails instead. How about the second quarter? Could it still be heads? Could it still be tails? So also we want 2 branches off of that tails down there. If there was a third quarter, we'd stop branching off again, or a fourth quarter again, but we always said 2 quarters, so that's where we're going to stop. And let's think about each endpoint. So there's one endpoint, here's one, here's one, here's one. Those 4 endpoints will help me determine my entire sample space. Let's think about what it would take to get to each one. Like, what's the path that brings us to this endpoint? First quarter was
Heads.
heads, and the second was
That's a good.
also, okay, so heads and heads. And then let's think about our next endpoint and what path it would take to get there. That would be first quarter heads, second quarter tails. So heads and then tails. All of these together are going to make up our sample space. So if you'd rather, you could write them down here. Got 2 of the 4. Give you a second to fill in the other 2. And notice that they're slightly different. You might start to notice that we're making a distinction between the 2 quarters, like the first one versus the second one. In other words, we're considering heads and then tails different from tails and then heads. Yeah, that's our third one. And what will finish it off? Lastly would be tails, you got it. So we're able to see our sample space laid out in the diagram. That can be real helpful then when it comes to calculating probabilities. You're ready to think about that next, go for it. You might want to back up and check on anything about the tree or the sample space so far. So you might consider practicing a little bit of notation, like P for probability, parentheses for of, one tail. We noticed that our sample space has 4 combinations, 4 things in it, so we'll divide by 4. Not because this is page 4, right? But because there's 1, 2, 3, 4. And by the way, when it says 1 tail, they mean exactly 1. Not 1 or more, not at least 1, they mean exactly 1. So out of our combinations here, how many included 1 tail? 2? Yeah, the HT and the TH. So not that one, but this one and this one. We're not including the 2 tails, the TT, that's too many. So 2 out of the 4, as in 1/2 for 0.5. So that was just an example of a question we could answer. Now that it's all laid out, that we could answer any manner of questions about that particular scenario. So pretty helpful because it lets us know how big the sample space is and exactly what the elements are. Anybody want to double check anything about our tree or our probability there? Hey, when we flip over, there's another tree for you to try. Am I right? Yep. So flip on over if you're ready to try another tree diagram. Maybe thinking back to how we started, we said, let's try to break the scenario down into a sequence of events. And for each part, we'll have a set of branches. I use a little help finishing up the last page or getting started on the next one. Tree starts from a root, right? We break this down into parts. How many parts, different parts would you say there are? I'm thinking about like we have the blood type to take into account, so that might be one part, one set of branches. And we have the RH factor to take into account, so that might be another separate consideration, a separate set of branches. Remember, your tree doesn't have to grow sideways, however you think it would fit best. So as an example, I'll flip this one around. I'm hearing some 2s and some 4s and some 8s. That sounds promising. So if we started with the blood type, how many branches would we need off of the root? Got 4 blood types there, don't we? We need one for the A, one for the B, one for the AB, one for the O. So last time we started with the first quarter, this time we're starting with the blood type. And then from each of those, we want to represent the possible RH factors, positive or negative. So we've got a positive or negative coming off of each one of these. Oops, that's a positive and a positive. Now that we've taken both things into account, we're ready to look at our endpoints and see what path led us to each one. What kinds of things are in your sample space then? What's the first thing you have? A positive, great. And a negative. So 2 of the 8 sounds like A altogether. Nice. Sometimes folks say that it reminds them a little bit of something from a science class, maybe biology. Might be similar, but I haven't seen anything out there that's exactly the same. So try not to lump it together with something already. Make sure to distinguish it. And make sure that you got the root. So in other words, we don't want 4 little diagrams. We want one big diagram. Everything should be linked together. All going back to the root. Anybody want to double check anything there? Do you think there would have been a way to know that there were going to be 8 outcomes? Yeah. What did you notice along the way that came to 8?
4 times 2.
4 times 2. Yeah, we had 4 A, B kind of numbers. So 4 blood types here. And then we had 2 of the RH factors. 4 times 2 made 8. Yeah. Well, what we're going to talk about next is exactly that. There's something called the fundamental counting principle that will help us know that total number just from a bit of multiplying. So we wouldn't have the diagram at all. It wouldn't give us as much detail, but it would help us find the total. So 4 times 2 makes 8. How would it have worked back here with the quarters? We ended up with 4 in our sample space. How could we have done some multiplying to get that answer? Each quarter has 2 sides, right? So 2 possibilities on the first quarter and 2 on the second quarter. Heads or tails for quarter 1, heads or tails for quarter 2. So if we only needed the number and didn't have to have all that extra detail, the fundamental counting principle could be a big help. Anything we want to double check about our 2 times 2 or our 4 times 2 before we look it over some more? Down at the bottom of the page. So this will count the number. It won't tell us what they are. It'll just tell us how many. Let me give you a minute to read over what it says in the box there. Or the partial box kind of disappeared, didn't it? So it's meant to be a similar kind of situation where your big picture can be broken down into parts. And the idea is if we know the number of outcomes for each part, that's what all these K's represent. The number of outcomes for each part, we can just multiply those together to get our grand total. So it doesn't matter how many parts there are, you can multiply as many numbers as you need together. Don't let the strange looking formula throw you off. It's just meant to represent that we can multiply all these individual part numbers together to get our grand total. And we'll try it out with this radio station question in a sec. Anybody see anything big picture you'd like to ask before we give it a try? in a sequence of events where we can break it down into parts, and each part has a certain number of outcomes. We'll just multiply those individual numbers to get our total. Well, let me give you a second to read what it says here about the radio stations. And look at see in part A what it is we're trying to do. Radio station call letters. That's just like the name of the station, sort of. What do we have around here? KMOX, is that a radio station? Usually 4 letters starting with a K or a W. I'm gonna start with 4 blanks, representing the 4 letters. So a blank for the first letter, second letter, third letter. And in the blanks, I'm gonna try to put the number of options. Because I know once I have those parts figured out, I can just go back and multiply it all to get my total. So the name of a radio station is 4 letters. Let's start with 4 blanks. Says the letters have to start with a K or a W. I think that has to do with the Mississippi River right here. If you're east or west, starts with a K or a W. Well, with the rules of the game here, how many options do we have for the first letter? 2. K or W? 2, exactly. So let's say we picked one of those, K or W, to start our radio station name. Let's start to think about the second letter. How many options will we have for it? That means we're going to need to know how many letters in the alphabet. Do we know that? 26. Yeah, and then we consider that something's already happened here. How many different call letters can be made if repetitions are allowed? Okay, so no matter whether we pick the K or the W, it says we can use it again, right? Repetitions, repeated letters are allowed. What do you think we should put in that second blank then? 26. Yeah, we have the whole alphabet to choose from then, don't we? There's no restrictions like there were on the first letter, and we're allowed to repeat a letter that we've already used. Let me give you a second to think about what numbers you would put in those other 2 blanks and maybe multiply them together. Anybody like to double check our 2 or our 26 so far? Are there any restrictions on the third letter or the fourth letter? No, so do we still have the whole alphabet to choose from? Are you thinking more 26s then? These answers can get kind of big. When you're multiplying numbers, multiple numbers, the results get big quickly. Yeah, hold on.
6.
Because there's 26 letters in the alphabet.
Yeah, I got that, the second thing, but,
Why do we
Why?
use it again?
yes.
Well, there's no rules about the third letter. It looks like we still have the whole alphabet to choose from.
Okay,
And same with the fourth letter, we still have the whole alphabet to choose from.
okay. Gotcha.
So I'm coming up with 35,152. Just from multiplying those 4 little numbers together. We don't have a list of all 35,000 possible radio station names, right? Like our tree diagram. That'd be a pretty crazy diagram, by the way. 2 branches, and then off of each one, 26, and then off of each one, 26, and so forth. Lots of possible radio station names. We have a similar but slightly different question up next in part B. You're ready to jump in and give it a look? Go for it. Anything else we can help out with on part A first, though? we're still talking about 4 letters, so I'm still gonna start with 4 blanks. And in the blanks, I'm gonna try to put the number of options I have for each letter. And when we have that, we'll multiply and be done. What's kind of different about the question this time? You can't repeat. Yeah, repetitions are not allowed. So if we use a letter, we can't use it again. Needs to be 4 different letters in the end. What do you think about that first letter then? How many options would we have? Still 2, K or W? Alrighty. 24, 25. Yeah, what do we think? Do we want in the next blank a 24, a 25, a 26?
25.
25? Yeah, because the idea is we would have used 1 letter so far, right? And if we're not allowed to repeat that letter, that means we have 25 left to choose from. Sometimes people are tempted to put 24 because of a 2. But remember, you don't ever use both of those, right? It's either a K or a W. So we do have 2 choices for the first letter, but we don't use both of them. We've only used one or the other. And then once we've selected our second letter, how many options are we going to have for the third one? What do you think we want in this third blank? 24? Because at that point, you've then used 2 letters, haven't you? So there's 24 left. 25, 24, 23 to finish it off. That's right. Do you think with this extra requirement, we're going to end up with a bigger number or a smaller number? Smaller? And are you getting smaller? What are you getting? Like that, 600? Great. Yeah, sounds great. We didn't have quite as many letters to choose from, so a smaller final total. These problems can hit on any number of topics, so everyone's going to sound a little different at first, but they all are all similar in that we have parts and numbers we can multiply together to get our total. If you're ready to try some more, I've got 3 for you on the back of that page. Your turn to give it a go. You will help finishing up anything on this page first. Ready to check in with your neighbors as you decide on the strategy or get some answers? Oh,
No. Choose. Not using 1 of 6, you can choose from 6.
So times. Right?
Not a fraction. So times it and it's not a fraction. You can choose 6 items. You can choose 12. Or 1 is a 12. So by the end of it. So like, say you choose appetizer only, then entree 4, then 7, at least 1, however many. And that's what you're looking for. You're looking for how many you can get. So it's just. Well,
Just be one once. Small points and then.
What are the parts we could break that first one down into? The dinner's made up of appetizer, so that'd be one part. What else? And entree and a dessert.
There are 6 questions. True. Which means that there's only
Give
2
them a
questions.
nudge, you wanna check that we're thinking the same way? 3 numbers to multiply together on that first one? Feel free to check in with folks nearby as you're ready. And when you're in agreement, feeling good about your answer, see if you can help fill in some work and answers on the board over there for us. Anybody use a little help with anything? Something about us. Do we make fractions on this? No, probably. Yeah. You've actually represented that by this and this and this. Subtracting it. You can even ensure. Yeah, there you go. Okay, anybody could help us get number 1 filled in on the board? Just a little help on that first one.
Nope. Oh, you should still go up there. You're gonna do 2. See that? Thank you.
Everything's filled in on the board and I've copied it onto the screens. You might check in what you have so far versus what you're seeing there. So we mentioned that the dinner had an appetizer part, an entree part, and a dessert part. So multiplying those numbers of options together, like we had 6 choices for the appetizer, 12 for the entree, for the dessert. 576 looks great. But want to double check anything on that first one? Sometimes number 2 is a little tricky the first time you see something like this. Why 6 numbers? Why 6 blanks?
6 questions.
6 questions, okay, so for each question, we're wanting to think about the number of options. Why do we have 2 in each blank? True or false, 2 options for each question, that's right. So we're gonna multiply 6 2s together, and 64 looks great. So we wanna break the big picture down into parts, like the 6 questions. Think about the number of options for each part. And it looks like a winner. Anything we can help out with on number 2? Well, it mentions that we have a 4-digit code, so 4 blanks, 4 numbers. Why is there a 9 in the first blank? What do we know about the first digit?
It just
Can't be 0. Okay, so no 0. That means we're only able to choose from 1 through 9. So 9 options there. Any other restrictions on other digits? First one can be 0. Last one must be even. Yeah. So we think about a number being even. What does that mean? It means it could end in a 2 or a 4, a 6, an 8, or a 0, right? That's what even numbers end in. So that makes 5 choices for that one. Sometimes people don't include the 0. So just do notice here that they are including the 0, because I think you might see something similar on homework. And then why the 10s here where there's no restrictions? How do we have 10 digits? 1 through 9 is 9 digits. What's the 10th one? The 0 makes a 10th option. Yeah, so if there's no restrictions, we have all 10 digits to choose from. And 4,500 sounds great. If these didn't just click with you right away, don't worry. With a little practice, they all start to seem the same. And then you know you're on the right track when they all start to seem the same. Any last things we could help out with on this page? Anybody noticed anything else in the homework we want to make sure to have a look at?